Okay, hi, and welcome to our continuing discussion of regression. Last lecture we talked about simple linear regression, and now we're going to extend that concept to multiple regression. So after this module, or this part of the module, you should be able to accomplish these various things. And let's get started. You can see the notes right here, and here's the things we're going to go over, and we're going to take a look at these presentation slides. Don't forget that as you're watching this, you might want to try out any examples that are discussed, and also jot down any confusing areas, questions, or comments that you might have. Okay, so let's talk about the concept of multiple regression. Multiple regression is really just an extension of our concept of simple regression, where instead of using a single variable, we're going to use multiple independent variables. This opens up interesting possibilities, but also requires some further analysis that doesn't necessarily occur for simple linear regression. But basically the concepts are all the same, we're just extending it. So as I said, when you're finished with this, you should be able to develop a multiple regression model and interpret their coefficients, and to look at which independent variables are useful to include and which ones are not, and a very useful idea of including categorical variables. So the multiple regression model, and again, a model is just a mathematical representation of the relationship between the numerical variables that we're interested in. Actually, in this case, we're going to extend this to not just numerical variables, but just relationship between the dependent variable, which is going to be numerical, and several independent variables, which can be numerical or categorical. We'll get to that. So don't let this formula scare you. It's just a shorthand and a bunch of terms to mean basically what we've already discussed. So let's imagine the first part right here. The first part here is just the simple linear regression model that we've been talking about, the equation of a simple line, where we have y equals an intercept plus a slope times an independent variable. What we're going to allow ourselves to do is, instead of trying to use a single explanatory or independent variable to predict the dependent variable, we're going to allow other explanatory variables to occur. And so each explanatory variable that I have is going to be multiplied by a slope, and we're just going to simply add them. Now again, as models go, this is really, there's nothing to say that this is always the correct model or the right model to use. It's just a model. So our objective here is not to say this is the correct model, but to see how best we can use this and how good this model is in predicting our dependent variable from our independent variables. So we're going to refer to these are just indices here. It gets a little more complicated where you say x1i and x2i, but forget about the I for a moment. Just think about, we're trying to predict y as a function, or just as the sum of a constant, which is our intercept, plus a slope, beta 1, times an independent variable x1 plus another slope for an independent variable x2 plus all the different other slopes all the way up to, say, k independent variables. And then we're just going to add our usual correction random error term. The reason why we have the i's here is the i's represent the observations. So we have observations y1, and we'd have x11 and x21 and blah 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 up to x k1, and then we might have another independent observation y2, and then we'd have x12. So it just means that it's the independent variables that go with the observation 1 for the dependent variable 1, and then number 2, and then 3, and then 4 and 5. So this is actually the data. This is representing the model for the data. Previously we just sort of ignored the indices just to say it represents all the different ones. So again, don't make too much of this. It's not that big of a deal. The simple way to remember this is, look, we're just looking at the dependent variable as the sum of independent variables that can be adjusted by some constant that we call the slope, and then there's some constant that has nothing that's independent of all these. This is sort of a correction to bring it up or down. We'll look more closely at this a little bit later, but again, don't get scared of this. This is the model. You never actually have the model. The model just represents what we're estimating. So these are unknown. The independent, the intercept, and the slopes are all unknown, and as is the actual distribution of the random error. We don't know what that is. All we're going to be able to do is estimate these betas and estimate the distribution for this random error. Actually, we're going to assume in our most cases that this random error is normally distributed. So so these are the unknown things. When we estimate these values, the beta 0 through beta 1, beta 2, beta 3, and the properties of this random variable, we're going to get what is known as the coefficients. So we get the estimates. The estimates is going to give us an estimate for the model, and the estimate for the model just means we get coefficients b0, b1, b2, all the way to bk. So the estimate these the population things are the things that are unknown, the betas. These are the things that we can calculate from our sample data, and this is going to be the relationship for the estimate. You notice that there is no error term here because we're going to assume by the way that we do this that the average, on average, the error is 0. In other words, sometimes this estimate is going to over predict. It's going to predict it too high. Sometimes it's going to predict it too low. But on average, they're going to balance each other out, and it's going to be 0. So we don't actually add any error term here because we assume that the error on average is 0. Another way to look at that is you look at the average of all the predictions. The average of all the predictions. So that means you sum this all up and divide by the number of them, which is the same thing as summing all this up and dividing by the number of them, is going to be 0. This provides what is called an unbiased estimate. Again, it's not necessarily true that we have to do that, but that just is convenient for us to do that. We're going to use Excel to figure out what these things are. In particular, we're going to use Megastat to calculate this. Excel can actually calculate what these things are too using a least squared regression, but we're going to use Megastat because it provides the analysis for these things. So these would be the estimates for the slopes, this would be the estimate for the intercept, and of course this would be the predicted value of y, not the observed. Okay. So let's take a particular concrete example. Let's say that we are a distributor of frozen dessert pies and we want to evaluate the factors thought to influence demand. So we want to think about, well, what encourages people to buy our pies, or maybe might discourage them from buying our pies. So the dependent variable is going to be, let's say, the number of pie sales, how many pies we sell per week, let's just say. It could be per day or per month, whatever convenient units we want, but it's going to be pie sales, so it's a count. The independent variables, that's the thing that's going to explain pie sales. So this is what we'd like to predict. We would like to explain or predict pie sales using what price we charge for pies in dollars and how much we spend in advertising. Now, we sort of intuitively, based on the problem here, believe that the relationship between price and advertising and pie sales would be one would be positive, and the other would be negative. So, in other words, if I spend a lot, the more money I spend on advertising, the more people know about my pies, the more pie sales I should expect to have. So that would be a positive relationship between advertising and pie sales. where price would be perhaps negative, that the higher prices for my pies, the less people are going to be wanting to spend the money for my pies because maybe they think that their money is better spent elsewhere, or they don't have the money for it, whatever it is, that the higher the prices for my pies, the fewer pies I'm going to sell. So let's just say that I collect data for 15 weeks. And if we collect data for 15 weeks in sequence, this would be time series data. And if it's time series data, we have to again be careful about time series data versus randomly collected data. So let's assume that we have this time series data from week 1 through week 15, and we count how many pies we've sold, and we look at what our selling price was, and we look at how much we spend in hundreds of dollars on advertising. So we would estimate, our regression model, which isn't here, would say that sales is going to be equal to a population slope beta 0 plus a population slope beta 1 times price plus a population slope beta 2 times advertising plus some random error. So we're going to estimate those slopes and the intercept and assume that the error is on average 0 with B0, B1, and B2. So our job here is to use this data by using least squared regressions to find the best values for B0, B1, and B2 that fit this data. And then we look at that in sort of the least square sense. And you can look at that lecture on that I have on what is least squares regression to see more details on that if you're confused about it. So we might put that into Megastat, and if inputting it into Megastat, we might get some output that says that sales is going to be equal to this intercept, 306.53, and that's going to be in, of course, units of sales. So this isn't dollars, it's 306.53 pie sales. So this 0.53 obviously is a little superfluous. We might want to just round this up to make it 307, so 307 pies. And the interpretation of that, of course, is that when price is 0 and advertising is 0, this is the number of pies we expect to sell. But as things go, that doesn't make any sense because, well, we're not going to, if I make my pies priced 0, I'm probably going to sell a whole lot more than this because I'm just giving them away. And if I don't spend anything on advertising, people won't know about the pies. So 0 is probably not, for price and advertising, it's probably not, it doesn't make logical sense. And so in that case, this term here as an intercept doesn't have an interpretation. It's merely a correction factor. And if it's just a correction factor, you might as well leave in the decimal 0.53 because it doesn't actually have an interpretation in terms of the number of pies. It's just trying to make our estimate more accurate. And we see that we get a coefficient for price, or a slope for price, that is minus 24.98. And of course we interpret that in the same way that we interpret slopes, is that it's going to be that for every increase of price by $1, we expect the number of pies sold to decrease, because it's minus, by 24.98 pies. Again, now this is in terms of pies, so you could just round this up to, say, 25 pies. So for every dollar increase in pie price, we expect to sell about 25 fewer pies. Now there's another little technicality here, and then we have to talk about holding advertising constant. I'll get to that in a little bit. This coefficient here, of course, is the slope for advertising, and it's interpreted the same way, that for every dollar, or actually 1 unit increase. Now 1 unit increase in advertising is $100 because the units of advertising in my data was hundreds. So for every $100 increased spending on advertising, I would expect to send, because it's plus, I expect to sell about 74.13 more pies, or about 74 more pies. And again, I'd have to say holding price constant, and that's a bit of a technicality. I get an R squared here of 0.521, and again, that's just interpreted the same way as before. It's saying that 52% approximately, 52.1% of the variability in pie sales is explained by variability not just in price, but in price and advertising. So in other words, both price and advertising seem to explain about 52% of the variability. Now that leaves about 44.2 after adjusting. So we'll talk about what that means. But what's interesting here is that if I look at the 1 minus this, so I have about, 48. It leaves about 48% that's unexplained. So that means that pie sales, about 48% of the pie sales is not explained by price and advertising. That's kind of high, so that sort of leads us to believe that there's another factor out there, or at least maybe more than one factor, that explains pie sales. The rule of thumb is if there's more than 10%, in other words, if you don't have an R-square of at least 90%, you're probably looking for some other explanatory variables. The adjusted R-square is going to be the value of the of the percentage of sold of variability in pie sales based on the variability of price and advertising when I account for the fact that I added an additional variable here called advertising or price. I had the fact that I have two of these things. So I also need to adjust not just for the number of variables, that's that price and advertising, but also the sample size. The issue here is that if I have a small number of data points and a large number of explanatory variables, then it becomes very easy to get a high R-squared because those points will naturally be able to fit in to those different variables. I have more room or more degrees of freedom. Another way to think about it is like, well, if I have a bunch of clothes, the amount of clothes that I can stuff into a closet is dependent on the size of the closet. Also, the number of closets that I have. So if I add another closet, I should be able to stuff more clothes in there. And because I can stuff more clothes in there, I can sort of organize it better and make it more neat. And as a result, I get this sort of artificial inflation. So the adjusted R-square attempts to take that into account by deducting some of the percentage of variability based on how many variables I have and the amount of data that I have. Now the R here is going to be the multiple R. I'll explain that a little bit later. And the standard error is the same thing. It's just the typical error in the number of sales. So on average, I would expect to have an error. I'll be off by the number of pies per week of about 47.43, or say 47 or maybe 48 pies plus or minus. The ANOVA table is the same as before. We get a p-value here that answers the question: does this model significantly predict pie sales? And the more specific way of thinking about that is there at least one of these, at least one of the independent variables that is a significant predictor of pie sales? It doesn't necessarily mean both, it just says at least one. So the fact that I have a low p-score here is 0.01. Well, it's somewhat low. It's less than, this is a little higher than 10%. So if I were looking for a 5%, right, I'd say 0.05, and this is less than 0.05. So I'm at least 95% confident that either price or advertising is a significant predictor of sales, or a relevant predictor. Now the regression output here gives us the same table as we had before, but you notice that instead of having one variable, I have both independent variables here. And the coefficients are still just the slopes, and the standard error of those are just the same. And the confidence intervals are still the confidence intervals of the slope. It's the same thing except for one for each. The one thing that's interesting is that I get a p-value for each of these, and the p-value for each of these corresponds to the t-test on whether the slope, this particular estimate for the slope, is this slope for price actually zero in the population or not? And so that would be, is this slope zero or not? So that's the same thing as going back here and testing the hypothesis. So say our model is saying that here's the population slope for price and here's the population slope for advertising. It's saying, is beta 1 equal to 0? And then the other one is beta 2 equal to 0. So here it just says, are any of them non-zero? Are any of the slopes non-zero? This one says, in particular, is this one 0? And you see that both of these are both less than 0.05, so at least at the 95% confidence level or 5% significance level, both price and advertising are significant predictors of pie sales. What's interesting to note here is that you see how this p-value is smaller for the combined than either of these alone. So this p-value is always going, if there's something significant here, if this is significant, then at least one of these is going to be significant too. Significant meaning less than 0.05 if that's my test for significance. Okay, so being more specific about that, let's interpret these coefficients for this particular example. Again, just to review, this is our estimate. It's the same thing as our other regression estimate, except for now I have both price and advertising. This is the slope. That's a slope for price. That's a slope for advertising. And this is the intercept where this is 0 and that is 0. So if I had to interpret this slope here, it just says that because it's negative again, that my pie sales will decrease by approximately 25 pies per week for every dollar increase in selling price. And again, I have to say holding constant the amount of advertising. And similarly, this is interpreted, the same way for a slope. So what's this business about holding advertising constant and holding price constant? Well, the issue here is that if I'm talking about increasing price by $1 and that this happens to be the change, then that gives me a decrease in number of pies. But the problem is that if this value of advertising changes, then the number of sales of pies also change. So when I'm interpreting this, I actually have to technically say advertising is saying the same. So for every value of advertising, for any value of advertising, as long as it doesn't change, the interpretation of this slope for price is that. So again, the problem is that if I change advertising, then the number of pie sales change. So that would change the interpretation of this. So we have to say holding it constant. Again, it's kind of a technicality, but it's an important one, that whenever you talk about the interpretation of the slope in a multiple regression, you need to talk about holding the other variables constant. How would you use the equation to predict pie sales? Well, just the same way we did before. Just plug in the numbers. Let's just say that I have a selling price of pies of $5.50, and I'm advertising with $350 that week. What would be the predicted number of pie sales? Just plug in the $5.50 for the price, that's there. Plug in $3.50 for the advertising there, and then just calculate it all up. And I end up getting 428.62 pies, or approximately 429 pies. Notice that you got to be careful about the units. Remember, the advertising was in hundreds, right? So when I plug in the advertising here, because the data was in hundreds, I can't plug in 350 here, because that would be $350,000, which is way too much. So I have to convert my 350 into hundreds, which is going to be 3.5, because that's what my units of in the data were. So you have to use the same units. To make the predictions using Excel and Megastat, you just plug it in. Just the same as we had before. We input our ranges, and our ranges are going to be now all the rows for, so you see how it says C to D here? So the independent variables now includes 2 columns, not just one. Of course, the dependent variable, what I'm predicting, is going to still be just a single column. And then the predictor values from the spreadsheets, you just select, again, a range. This is C and D here. We select all the ones that I want. And, we're going to pick the usual things here. And we're also going to check variance inflation factor to check for some particular problems that might occur. So in Megastat, when I get predictions from Megastat, not only does it give me the predicted values from the calculations, but it gives me the prediction intervals, lower and upper, for each value that I'm predicting. And as usual, I also get the confidence interval, so the usual confidence interval. So that's on average. So this would be the mean, and this would be the particular, as before. So once again, let's go back to the adjusted R-squared. Some people get confused about that. Whenever I add a new variable to the model, the R-squared is never going to decrease. And so the problem with that is that, and that's because I'm adding more room, another degree of freedom for the data to fit into. So it's going to pretend like it's explaining more, but we want to know when it's really explaining more. So one way and the problem is if we're comparing models, we want to know, well, if we add a new variable, does it actually explain more of the variability? In other words, is it a better predictor because it's going to have a stronger relationship than when we don't? So we don't want to add things that don't explain more variability. So what we do is we look at the adjusted R-squared, and the adjusted R-squared sort of takes out the amount that would be increased just by adding a junk variable. So if I just added a variable that did nothing, that would increase the R-squared by a certain amount, so the adjusted R-squared just decreases it by that amount. So the adjusted R-squared should always be smaller than the R-square. And what we want to do is, for comparing different models, meaning different numbers of explanatory variables or independent variables, we would want to choose the one with the highest adjusted R-squared, not necessarily the one with the highest R-squared, because if we just keep adding dumb variables that do nothing, we can increase the R-squared. So the f-test for overall significance, that's the ANOVA, again, is that first p-value in the ANOVA table, and it just shows it tests the hypothesis, are any of the slopes not equal to 0? So the null would be all of them are equal to 0, which means no relationship. None of those variables explain anything, and the alternative would be at least 1. And 1 being explanatory means that the slope is not equal to 0, and of course we'd want to know which one that is. So again, we got that p-value from the ANOVA table. This is using the f-test. The f-test is just a particular distribution that it's getting the p-value from. So if you're asked to write the hypothesis for overall significance, that means does this model actually predict? The hypothesis would be the null, all the slopes in our particular model is beta 1 and equals beta 2 equals 0. In other words, the population slope for price is equal to the population slope for advertising is equal to 0. The alternative would be either one or the other, but not both are 0. And if we say test it at significance of 0.05, we get a p-value of 0.012. That's less than that. We would say, we can be 1 minus this confident, 98.8% confident, that one of these is not equal to 0 in the population, and so at least we conclude that at least one of the independent variables, because these are the slopes for price and advertising, so at least one of advertising or slope is a significant predictor. Of course, it doesn't tell you which one. To look at the individual ones, we can do a t-test for individual slopes, and with the hypothesis would just see that particular slope is equal to 0 versus that particular slope is not equal to 0. In other words, if the slope for, say, price is not equal to 0, then that would mean that price is a significant predictor of sales. We see the results for that in Megastat by, again, looking at the p-values under the regression output. And so this is the test of this hypothesis for price, and this is the one for advertising. So slope for price, p-value is 0.0398, which is less than 0.05. So we're at least 95% confident. How confident? 1 minus this confident. And same for advertising. This is also less than 0.05, so this is also considered a significant predictor. Again, you get to choose what significance means. Significance means that I'm less than the level of significance that I chose. Conventionally, or sort of a rule of thumb, is again you pick levels of significance between 0.1 and 0.01, or 10%, 5%, and 1% are the convenient ones. So again, from our particular example, we got one of the p-values. I guess it was for price. See, is 0.0398, and the advertising one is 0.0145. And so we can say 1 minus this 96.02% confident that price is related. Oh, and by the way, it's saying holding advertising constant, not confident. This is a typo. This should be constant. And we can be 1 minus this p-value confident that advertising is related to sales holding price constant. See, that one's not correct. So in other words, there's evidence that both of these guys, both price and advertising, are significant, and we probably want to use them both in our model. The confidence interval for the slope, again, is just the same thing for the simple linear regression case, except for I just interpret it for each independent variable. The only hiccup here is that, once again, if you're interpreting the confidence interval for the slope, you still have to say holding the other variables constant. So for example, let's look at price. The weekly sales, if I increase weekly sales, so it's minus 48.5763. So if I increase price by $1, my pie sales will decrease by decrease by about 48.5763, or it'll decrease by about 49 pies. That's on the low end, and then on the high end, so I will either decrease from, with 95% confidence, I'll decrease between 48, say 49 pies and 1 pie. So let me repeat that. With 95% confidence, my pie sales will decrease by 48.58, and between 48.58 and 1.37. I don't ever talk about the minus. I just use the word decrease to mean minus. It's just kind of awkward to say my pie sales will increase by minus 48.57. That kind of is weird. And we have to say holding advertising constant. Again, because if advertising were not held constant, it would change my prediction, which would change my impact of this. So we have to say we're holding it constant, meaning we're not changing it. Again, just a technicality. Now, when we assume that the residuals, or the errors, which is going to be the observed minus the predicted, we're going to, so we call it, say, the EI, we're going to look at the distribution of these, and we assume that the distribution of the residuals are going to be normally distributed, or bell-shaped. So we're going to make the same assumption as simple regression. We're also going to assume that not only is it normally distributed, but it has mean zero, meaning that I'm not over-predicting or under-predicting, an unbiased prediction. So the mean of the residuals, if I took the sum and divided by the total of these, is going to be 0. Of course, that means that that doesn't mean the variability is going to be 0. The variability, of course, is going to change, is going to be something, and that's what we call the standard error. We're going to assume that the equation is linear for all of the independent variables. So in our example, we had price and advertising. We're going to look to see whether the residuals are linear for both price and for advertising separately, not at the same time. And that the errors have constant variability. And the other thing that we have to look at again is not only normally distributed, but the errors are independent over time. Now this is important because in our example we collected our pie sales per week, so that was time series data. So it's possible that the sales of pies are not independent over time. Say for example, if I'm selling around Thanksgiving, then I'm going to tend to sell more pies if I'm collecting data around Thanksgiving than outside of Thanksgiving. So that would mean they're not necessarily independent, but I need to assume that the errors are independent over time, which is the same thing as that the data was collected independently. Okay. The residuals plot that I'm going to use for our pie sales example, if I want to check for, say, linearity, is I would just look at the residuals versus the x1, which is price, and I would check to see if it looks linear. Or I could check to see if there's a polynomial thing that's greater than has an r-squared 0.2, like our rule of thumb says. Then I might look at the residuals versus advertising and see if it looks linear. And then I would look at the residuals versus the predicted y, just like I did in the simple case. Then I look at the residuals to see if they're normal by looking at a normal probability plot or the skewness or kurtosis. And then I would plot the residuals over time and see if I see any snaky stuff, or do a Durbin-Watson. So in terms of checking assumptions, this one, and this one are identical to the simple case. What I'm adding is I have to look for linearity in each one of the variables here. Of course, there's going to be a few other things I'm going to need to check too, but we'll get to that. So using dummy variables. Dummy variables are when I want to add a categorical variable into my model, and I want to see, does a categorical variable have an effect, and if so, what effect does it have? So because I'm dealing with numerical data, what I need to do is somehow convert this into a numerical impact from the categorical variables. So a dummy variable means I'm going to put a stand in for the thing, for the variable. So let's just say I have categorical variables with two levels, say yes or no, male or female, before or after merger. So this would be a categorical variable with two groups. What we're going to do is code the group, one of the groups with the value 0, say yes, and we'll code the other one with the opposite, say no, equal to 1. The idea is that what we want to do is we will code 1 with the category that we're interested in seeing if it has an impact. But it doesn't really matter, because if I know, I can always look at the impact of the other if I know the impact of 1, because there's only two groups. We'll talk about how to deal with more than two groups later. So this assumes that the slopes are somehow associated with the numerical independent variable, and they don't change with the value of the categorical variable. So in other words, it doesn't change the category, but it influences it. So if I do have more than yes or no, you can say I have yes, no, and maybe. Okay, yes, no, and maybe. Then what you can do is you can just add the categorical variable, a dummy variable, for each category of interest. So I'd add a code of yes 1, and then others would be 0. And then I'd add another one that says no is 1 and others 0. And the other one would be maybe is 1 and others are 0. So I'll take a look at that in a little bit later. So in other words, you just add more dummy variables if you have more categories. So let's take a look at our pie example. One thing we might suspect is that during holidays like Thanksgiving or Christmas, we tend to sell more pies. So we want to test to see if that's true. We want to see if that relationship holds. So what we're going to do is define a new independent variable. We'll call it x2, which is going to represent whether there's a holiday or not. And this is going to be a dummy variable. We'll code it as 1 if the holiday occurred during that week of sales, and we'll use the value 0 if it didn't. So what we do is we put that into the model by, it looks like this. When x2 is equal to 1, in other words, there is a holiday, then what happens is we get our usual formula. Let's just say b0 b1x plus b2 1. So now this is just adding in, I'm not looking at my, I'm just looking at price. I'm looking at price and holiday, no holiday. Okay, so price is x1 and pie sales is y, and x2 is going to holiday. I'm going to ignore advertising for the moment. So when it's equal to 1, what happens is that I end up, this formula ends up giving just b0 plus b2. There's no x here, right? Because x is either 0 or 1, right? x2 is equal to either 0 or 1. So in this case, when it's 1, it just leaves the slope. And then the slope just combines with that. Okay, and so what we have, the same slope happens, but what happens is that my y-intercept effectively increases, or might decrease if it's minus. When there's no holiday, what happens is I'm multiplying by 0 here, and so it just disappears, and so I'm left with just the same slope and the same intercept that I had before. Just like with any independent variable, I would want to test the hypothesis to see whether the slope is significant or not. So if I have a p-value for beta 2, which is the slope for the dummy variable for holiday, no holiday, then I would say if the p-value is less than 0.05, I might say, well, that should be, that means that it is significant, and so I would say that holiday is a significant predictor of pie sales. Otherwise, if the p-value is large, I would say there isn't evidence that holiday has that. So again, it's just the same thing, but the interpretation is much easier for the slope, you'll see. So let's interpret the slope value for that. Let's just say that in my pie sales, I get an intercept of 300, and I get a slope for price of minus 30, and I get a slope for holiday, which is our dummy variable, of 15. How would we interpret that? Well, what it says is that when holiday is equal to 1, so there's no such thing as increasing it by 1, because this holiday variable is either 0 or 1. It's not anything more than that or less than that. It's either 0 or 1. So I'd say when there is a holiday, or in other words, holiday equals 1, I would expect to sell, see it's plus here, 15 more pies. So I'd expect to increase my sales by 15 pies. When there's no holiday, this is 0, so I don't have any increase at all. So on average, sales were 15 times greater during a holiday than when there was no holiday. So this talks about the difference, the increase or decrease in number of pies sold when there's a holiday compared to when there isn't. And of course, we have to hold price constant. So if price changes, that would change this impact. So we say holding price constant. So that's about it. We'll go through some more particular detailed examples. It's not that much different than the simple case, except for that we have a lot more things to check, we have a lot more things to interpret, and there's going to be some special situations which we'll deal with later. So keep those questions, jot down those questions for me, and I'll see you in class with some examples.